Okay, so I'll start to give you some incentive and some historical perspective. I want to talk first about the three main scientific discoveries of the last century that led us to modern technology in general and to quantum computing in particular. So, so let's begin with the first discovery. So that discovery dates back to the late 1900, 18, to the 19th century, 1862. So the gentleman you see here is James Clerk Maxwell, and he was playing with the equations of electricity and magnetism that were formed by Faraday. You don't have to understand, don't worry, the equations, but they tell you what happens when you change electric field, when you run current, what happens to the magnetic field, what happens to the electric field. And simply from aesthetic reasons, he decided to play with these equations and try to make them look more symmetric in the way that the electric field would affect the magnetic field in the same way that the magnetic field is affecting the electric. And he guessed out of nowhere this new term. And once you do that, it's really short derivation to reach a wave equation. So uh, what is a wave equation? Something that moves in time. And James was pretty excited because at that equation, you can actually see what is the speed of that wave of electricity and magnetism. And he was surprised to find that the speed of that wave was a constant of nature related to the electrical and magnetical constants. And that constant of nature was actually turned out to be the speed of light. So think about that moment in history. No one knew until then what light was. Uh, Not Newton, not Aristo. And the people argued, is it a current of something? And he discovered what it is. It's a wave, it's an electromagnetic wave. This is the reason we call light an electromagnetic wave, like radio, like radar, like microwave oven. So all of these are electromagnetic waves. And so besides being very exciting, this is the first time in nature that, and in history, that a speed of something is fixed, is a constant of nature. No matter if you're running towards light or running away from light, you will see that light coming towards you at the same speed. And that was very weird. And the first person to explain this was actually Albert Einstein. And in 1905, 40 years later, and the only way to explain that was by realizing that time and distances were relative. So if somebody's moving at some speed towards you, that somebody's clock is moving actually slower. And so speed and also gravity, they warp time and space. This was really crazy, and indeed, no one believed it at first, and there were quite a few years before the scientific community started to accept these terms. So this is, of course, the theory of relativity, and and this is the reason, or without knowing the theories of relativity, we couldn't have had GPS navigation. We wouldn't know time accurately enough, uh, and we wouldn't understand space and time at all. And indeed, uh, today, all modern technology, and certainly what we consider to be very important, like nuclear power or even nuclear weapons, all these would not be possible if we didn't discover that law of nature, Einstein, that law of nature. So this is, of course, relativity. Both space and time are warped, changed by speed and by mass. So So this was quite a shocking revelation. And interestingly, it happened in parallel to another revelation which changed our view of the universe. And that second discovery is actually related to the question of how things emit light. So you take some iron and you put it in the fire or in the oven, and it starts glowing. So surprisingly, this was not something that scientists could easily explain. The equations didn't turn out right. And the first one to be able to explain properly what color of light is going to be emitted, how much, at what temperature, the only one who solved this problem was Max Planck. And he was actually making some, again, mathematical assumption that he wasn't sure that is even connected to reality. He assumed that light is not emitted in a continuous manner. He assumed that any energy is actually emitted in quanta, in units, in like particles. And if he assumed that that unit is proportional, the amount of energy in each such unit uh, is proportional to the frequency of that wave, then boom, he got the equation right. And and as he was playing with the constant, what is the ratio between frequency and energy, he came up with what we call today Planck's constant. Now, once again, I ask you to think about it for a minute. He didn't know, of course, that it's going to be called after his name. He discovered the constant of nature. And we have, when I teach it in class, I tell my students, we have to feel some sense of awe. If you're a religious person, then who made that? Who decided what is that constant? It's God. It's the very creation that decided what is the value of that constant. It's very, very small, but it's not zero. Um, so and the one who gave it the proper explanation was once again Einstein. He called it, wow, it looks like particles, isn't it? So light is indeed a wave, but the energy is actually a stream of particles. Um, Energy comes in discrete quanta. So this is indeed the source of the name quantum mechanics. It comes from the word quanta, which means that energy comes in discrete units, one by one. And in the development of quantum mechanics, there were many people involved, not like in the relativity theory, where Albert Einstein was the leader of that theory. And of course, people like Erwin Schrödinger and others. And eventually it took a couple of decades to formalize what we call today quantum mechanics. And so if you have to explain what are quantum mechanics, what is quantum mechanics? So uh, everything, the quantum mechanics explains everything in the universe by a wave. If you look at Schrödinger's equation, it's a wave equation. Actually, it's a very intuitive one, even if it doesn't look so. I even explained it once in my son's kindergarten, believe it or not. I gave it a try. So actually, what's written here is the very definition of energy. And I asked the kids, what is energy? And they started jumping and shouting. And very quickly realized that energy is the ability to do something, whatever, sing, think about a hard problem, or run. And then I asked them, okay, so energy is what allows you to do something, but what is doing? And after some encouragement, they reached the conclusion that doing is changing things. So if you don't do anything, nothing is changed. But no matter what you do, it always corresponds to some change in reality. If you run, you move from one place to the other. If you solve a problem, you solve that problem. So something changed in time. And this is actually exactly what's written here. So this is Schrodinger's equation. On the left side, you see d to dt, the change in time. And on the right side, you see h, or the Hamiltonian of the same thing, which is actually the energy. So this is the very definition of energy, the rate of change in time. And this uh, uh, very, very simple equation explained marvelously everything in nature. But it's not only a wave, as I mentioned earlier, the trick or the crucial point there is that the energy in any wave comes in discrete units, 1, 2, 0, but never 1.5, 2.5, never. Always round numbers. And this looks like particles. And as it turns out, there are two kinds of waves in the universe. One kind is called, okay, actually, so one kind is called fermions. And in those waves, we can have only one unit of energy, the electron, the proton, the neutron. So although all those things, we call them a particle, are actually waves in which we are allowed to have only one unit of energy. So they look like a particle. And the other uh, types of waves in the universe are bosons, and there you can have as many units of energy as you want. You can have as many photons, energies of light in a pulse of light. You can have as many phonons in a guitar string that oscillates. So those things that are allowed to have as many units of energy as we want look like waves. And the others that can have only one, they look like particles, but it's the same thing. So there's actually, I heard, so people like to say, the electron is both a wave and a particle. Is there a wave-particle duality? No, there's no duality. In the same way that there's no duality between a car and passengers in the car. So the wave, if I send a pulse of light, the wave is the car. How many photons, how many units of energy are in there? This is like the passengers in the car. So there's no wave particle duality, the same way there's no train passengers duality. So this is the relation between the waves and the particles. Particles are just how many units of energy are in that wave. So if you have to explain quantum mechanics, in 2 minutes, this is quantum mechanics. So the amazing thing about quantum mechanics was that it became the most accurate description of the universe we ever had by far. It's the best we ever had as mankind ever had. And to emphasize or to demonstrate this accuracy, I want to show you a video of a friend of mine. His name is Chin-Wen Chow, but his American name is James. We did postdoc together in Caltech, and today he's a scientist at NIST in Boulder, Colorado. And back in 2000, I think 18, or between 2010 and 2018, he was responsible for the best atomic clock. So what is an atomic clock? It was actually based on an ion. That ion is somewhere here on the table. You don't see it behind all those lasers. And what he's doing there in the video that I'm going to show you, he's going to raise the table using jacks, the same jacks that use to lift a car. He raises the table by a few inches, and you see that time speeds up This is the number you're going to see on top. So in some sense, this is a combined demonstration of the theory of relativity that says that closer to Earth, time moves slower than further away from Earth, and quantum mechanics, which gives us the ability to measure accurately that time because we understand the frequencies of the electrons so well. So here, I'm going to play the video. Look at the number on the top. So this is a time-lapse video. You see the table is raised and time is gradually moving faster. That's amazing. That's really amazing. And then the table was setting. So this is a very impressive demonstration of how accurately quantum mechanics combined with the theory of relativity allow us to predict what happens in nature. Actually, time moves slower here than here. Just a separation of 1 inch is measurable today, thanks to quantum mechanics. So, in fact, everything today, all modern technology is already governed by quantum mechanics. We wouldn't have, GPS, satellites, imaging, microscope, electron microscope images, specifically of the coronavirus here, uh, and of course, computers. So today's computers, the computer that I'm using is actually a quantum computer in the sense that we wouldn't be able to build so many transistors without understanding that the electron is a unit of energy in a wave. The separation between the electrodes in TSMC's, for example, chips. So the separation between the gates, the electrodes of the transistors in those CPUs is roughly, a few nanometers, which is tens of atoms. You see the atoms there in the picture. So, and of course, seeing that picture is also a demonstration of quantum mechanics. So we wouldn't have today's computers without understanding quantum mechanics, without quantum mechanics. So in that sense, all the AI revolution, which is changing our world, is actually a spin-off of quantum mechanics. So this is quite a view on how things develop, right? So we wouldn't have all those computers without one specific scientific discovery in physics. So that's indeed the second the discovery. And all that buildup was to reach the third discovery. So actually, that's a very recent one. It was proved only in 1981. I don't know about you, but I was quite alive by then. um, so I was 10 years old when they realized that this discovery is not a fiction, is actually correct. So in some way, in some sense, this is the most recent time in mankind's history that our view of the universe was fundamentally altered. Um, and uh, and it relates to quantum mechanics, and it's part of quantum mechanics. And it begins with a problem in quantum mechanics. Quantum mechanics may be accurate, but it introduces some sense or some level of uncertainty because it describes everything like a wave. So a wave is something that lives in more than you can measure wave in more than one aspect always because it's always something continuous. For example, if I have a very, very short wave in time, very, very short noise, like that, can you tell me what it was the note? What was the frequency of that clap? You can't. It wasn't do, re, mi, or fa. It was a combination of many, many frequencies because it was very short. So that's the uncertainty. That's the uncertainty principle. And if I want a very, very accurate note that has only narrow, very well-defined frequency, I have to do something like a very long note. Then I know the frequency, but that musical note is very, very long in time. So you see, once I treat all the universe in the language of waves, I have to accept that one description can be accurate and the other can be less accurate, because this is just the math of the way the math of waves go. And again, the person who didn't like it, well, he appears many times. Albert Einstein received one Nobel, and annoyingly on almost the wrong thing, by the way, at least in his view. But he sometimes I think that Albert Einstein, well, received his knowledge from aliens, because he he reached so many conclusions and discoveries. To some of them he didn't believe. In some of them he didn't believe himself. So it's like, the aliens gave him that and he said that can't be true. So this is one of those things. So together with two other Jewish scientists, this is another pinnacle of Jewish ingenuity. Einstein, Podolsky, and Rosen. In 1935, they thought they found the proof of how that quantum mechanics is wrong, or at least incomplete. And the example they gave was, well, you say that according to quantum mechanics, you can have two things that are uncertain. Each one of them is not fully defined. Okay, but according to the same math, according to your quantum mechanics, actually, we can have two things that are each uncertain, but they are the same or exactly opposite. They are completely correlated. So, how we do in Israel, do like this? This doesn't make sense, right? Somebody's cheating. How can I be coordinated with somebody else if I didn't, if I didn't write down, if I didn't, if we didn't prepare it together, if I don't have a knowledge about myself, how can I be completely correlated with another thing, with another person? So it's like having two coins that each is uncertain, but when we throw them, one of them falls on heads and the other on tails. If these coins are fair, it doesn't seem possible. But this is what quantum mechanics predicted, and Einstein, Podolsky, and Rosen. This is why it's called the EPR paradox. Einstein, Podolsky, and Rosen. They called it spooky action at a distance, and they concluded it's completely impossible, and therefore quantum mechanics is wrong. And so how can you have correlation without coordination? Only if things were predetermined, which quantum mechanics says that they're not. And for those of you, who know Hebrew, it actually like a sentence from the book of Amos, Sefer Amos, "Hayelchu shnayim yachdav bilti im noadu." So it's a question in the book of Amos, which is meant to be a rhetorical one. Can two people go together to the same place if they didn't coordinate before that? And it's meant to be a rhetorical question, and the answer is, of course not. So for 30 years, this problem remained a philosophical one. They thought it's a philosophical problem and not something that needs to be discussed in science. Sort of like, again, like everything is predicted by God, but the choice is ours, which is another saying in Hebrew, "Hakol tzafui v'reshut netuna," which is from the Mishnah. So maybe it's just a philosophical problem. It's not something that needs to be discussed in mathematical terms. But that thought actually withheld science for 30 years because it actually can be measured. you can actually frame that question in math. And the person to do that 30 years later was John Stuart Bell, a mathematician, and he wanted to prove Einstein correct. That's what he thought he was doing. And he came up with a very, very simple, really, it's one line of math that tells you that, well, if Einstein is correct and the things are actually certain, but we don't know them, and quantum mechanics is wrong, then there's a limit on the correlations. There's a limit on the correlations that you can have if if you have a deterministic world. And however, if quantum mechanics is right, you can exceed the correlations can extend beyond what is possible in a deterministic world. It was one line, and it shocked the world, and it took 17 years, I think, before Hélène Aspect and Philippe Grandier in 1981, two French scientists measured it with photons and realized that John Stuart Bell was wrong in saying that Einstein was right, uh, and Einstein was wrong in saying that quantum mechanics is wrong. Or to wrap it up, um, Einstein, Podolsky, and Rosen did point at the most curious thing in quantum mechanics, but it's correct. It's a correct thing. Quantum mechanics allows two things to be correlated without them being determined. So this is uncertain, but they are together. This is called entanglement, and it was very late. So the people who proved it, like Helena Span and Anton Zeilinger, they got the Nobel in just 4 years ago for this discovery, for proving that John Stuart Bell is no longer alive, so he didn't get that Nobel. But this turns out to be the birth, or the third discovery that is the birth of quantum information, quantum computers. And what it actually says about the world is something very, very fundamental. The universe is not local. So we can have two coins, one in the United States, one in Israel, and both are random. You can come up with all the tests you want, all the lab exams, and still and prove that they're random, but they will be correlated. If one falls on heads, the other falls on tails. So this seems so they both share the same random variable, even they're not at the same place. The universe is not local. That's very weird. It's spooky action at a distance. We agree. So for one thing, you could use that for encryption. This is indeed the birth of the field we call today quantum key distribution. And the Chinese even have a satellite in orbit that sends such correlated photons to two very, very distant customers, for example, in Vienna and Beijing. And they have random numbers, 0 or 1, but correlated. If one has 0, the other has 1. So this is what we call today quantum cryptography. You cannot break that because it's not based on some mathematical problem that you need to solve. Nature itself guarantees both the fact that it's random, so you can't predict it, you can't eavesdrop to it, but they're correlated. And if you do listen, you ruin the correlations, and and that eavesdropping is detected. So this is quantum key distribution, or quantum cryptography. All the world by now is sorry, I'll touch that later. But something even more fundamental about this non-locality is about the concept of information. Think about the following situation. Every morning, I'm sending you an envelope with two coins. And when you tear the envelope, one of them falls on heads, the other falls on tails. Did I send you information. Can you decide, for example, if to go to work or to go to the beach based on what I sent you in that envelope? Right? So you get an envelope, you tear it, boom, two coins fall, one heads, one tails. Can you make a decision based upon that information? No, there's no information because you always get the same thing. So two coins have no information. However, if I send those two coins to you and your twin brother or sister, if you have one, to your identical twin, now each of you gets only one coin. And each of you can decide if it's on heads, we go to the beach. If it's tails, we go to work. So, did you realize what happened just now? One coin, if I give you an envelope with two coins in that very, very interesting state, I didn't give you information. But if I take that envelope, tear it apart to two halves, and give you one half and your twin brother the other, you do get information. So how can information be something? How can half a book have more information than the entire book? This is impossible. We have to redefine information is is not what we think it is. And in some sense, this is the shortest explanation I can give to why quantum computers work. Quantum computers work because the math of information is different than what we thought. So, for example, in that example I give you here, n versus square root of n, this is the problem of looking in n possible solutions. N can be a million or a billion or, or tera. And a regular computer would have to run over all the million different possible answers. But a quantum computer can run only square root of n times. So if it's million different possible answers, a quantum computers would have to do the calculation only 1,000 times, not a million. And if it's and if it's tera, 10 to the 12, then a quantum computer would be 1,000,000 times faster than a regular one. So that's how quantum computers win the game. They win the game by cheating, not by running faster. The math of information is different. And an even more shocking algorithm was the algorithm discovered by Peter Shor, both Lovegrove and Shor from Bell Labs. So the algorithm of Shor allows you to break the RSA, the encryption of the RSA. So the encryption that we use for public key distribution, for example, between us and the bank, is related to solving, to finding the fact, to factorizing large numbers. You have a very, very large number, and you try to find out what are the two numbers that compose that big number if you multiply them. And apparently, this is something that's very hard to do in regular math. This is why the RSA encryption works. But in quantum computation, it's actually much, much shorter. So you can have an RSA key that would take billions of years to break, which is what we have today, practically. But the quantum computer has the potential to break it in minutes. So that's amazing. And that started the whole quantum computing era. And actually factorizing numbers for breaking the RSA is the most solid proof of an algorithm we have. But everybody believes, there are very, very good reasons to believe that there are many other complex problems that will be solved by quantum computers, like most of them chemical simulations, chemical questions for drug, for drug development, for CO2 sequestration, to developing better batteries, etc. So this is the potential. And let me, spend the last 10 minutes about the state, 10 to 15 minutes about the state of the art of technology today. So are we there yet? We know it has a potential, but are we there yet? So not everything is, some of the examples I gave are a year or 2 years not updated, but believe me, as you're going to see, not much is really changing when you count it properly. So this is a demonstration from like a year and a half ago, right? Um, and this is the Willow chip by Google, and they admit that it can't break cryptography. So, and why is that? The reason is that the qubits, the quantum bits that we can build today, a quantum bit is something very, very fragile. It's something that can be 0 and 1 at the same time. It can be 0 plus 1 or 0 minus 1, not necessarily 0 or 1. So this is what makes them powerful. However, they have to be something, a very, very weak effect in nature. So nothing measures them, nothing interacts with them. So if it was something with a lot of energy, then you could measure it from distance, and you wouldn't have a qubit, you would have a bit. So for this reason, because it relies on a very, very weak and fragile effect, the error rate of quantum bits is very high. 1 in 1,000, for example, or 1 in 10,000. Well, this is so far compared to the rate of error in modern computers. The chips we have today, the transistors we have today, their error rate is 1 to 10 to the 15. So, 12 orders of magnitude, sorry, less. So we must learn how to protect these qubits and how to make quantum error corrections. And as it turns out, that error correction is very, very costly. We need millions of qubits, not just hundreds, in order to allow these error correction codes. Why do we need so many? Because there are three ways that a qubit can actually go wrong. So a bit can go wrong, if a 0 turns 1. So I can repeat it many, many times and do majority vote. And that's how I protect a bit from errors. So I repeat it, let's say here 1, 2, 3, 4, 5, 7 times, 10 times. However, a qubit can have another type of error. It can turn from 0 to 1, or a 0 plus 1 can turn to 0 minus 1. So it's more complicated. So I need to add another level of duplication to protect from such errors. And how do I know that these errors occur? You check for some parity, but actually your measurement device is also very, very challenging because you need to measure a qubit. And your measurement device can be wrong. So there are three types of errors here, and every error correction code has to be three-dimensional. And as a result, you need thousands of qubits, of physical qubits, to protect one logical qubit good enough. So bear in mind, and whenever you see an example of some demonstration of quantum computing, bear in mind that technology needs to reach millions of qubits. So let's go over the technologies. The first were in 1995, ions. Dayan and Rainer Blatt, and later Chris Monroe, who was a postdoc with Dayan. And Dayan got the Nobel in 2012. We'll get back to that. So how do you make quantum computers with ions? So if you ask a physicist, physicists don't know the periodic table. Most of the atoms have too many electrons. Physicists know only and deal only with one column of the periodic table, the column that has only one electron, because this is something we can solve. All the others are too complex. So the way you do it with ions is you go to the second column that have two electrons and kick one out, kick one electron out. Now you have an ion with only one electron. So everybody's happy again, we can calculate it. So we shouldn't be surprised that all the quantum computers that run on ions use elements from the second column. And since they're charged, you can trap them, for example, on a chip in this image. And the way they communicate between them, you initialize them with lasers, and the way they communicate between them is by vibrations, actually, because they repel each other because they ions. So this is a very, very cool thing, and this mechanism was the first to be developed. So they are the first qubits to be demonstrated. The problem is that once you have many is more than dozens of ions, then the way they could vibrate become very, very noisy and random. You can't predict it. And this is the reason that today's ion computers, even what I consider to be, a leading, if not the leading company, Quantinuum, they have 96 qubits. So they are marvelous. They're amazing. They have amazing fidelity. They're very high quality. But after 3 decades, they're only at roughly 100 qubits. It's hard. It's hard. And remember, we need millions for commercially viable computers. The second type of qubits to be demonstrated were superconducting qubits. It's Michel Devoret, Nakamura, and John Martinez. And they used some LC circuits, electric circuit, that if you add some superconducting junction there, it changes the energy levels in a way that you can define a qubit there. It looked neat because it looks like a chip. Actually, also an ion quantum computer has a chip, that traps the ions. But it looks like a chip, and it really excited everyone. And it's the first time that you could see on something as big as a electrical circuit, which is very, very large, to see a quantum effect there. And that gave the Michel Devoret and John Martinez the Nobel just last year. So, but these qubits are very, very low energy. And so the quantum computer, actually, the CPU actually sits at the bottom of this dilution refrigerator that goes to, minus 273, almost the absolute zero. So the actual chip is here at the bottom. And this is the image that we all know, IBM, Google, etc. But once again, the largest number of qubits that were used in the calculation. So I think IBM had a chip of more than 1,000, but they never used more than a couple of hundreds in the calculation. So still, the number of qubits involved in the calculation is again in the hundreds. And all the best minds worldwide are dedicated at this task, and they have marvelous advances, but still after 3 decades, they as well are in the hundreds. This is the challenge, going to the million. We need million, we have hundreds. And similarly with neutral atoms, which came later. Vladan Vuletic and Misha Lukin from Harvard and MIT, Antoine Debreu from CNRS, and Ben Bloom from atom computing. So here, neutral atoms are used, and they have amazing demonstrations, but once again with hundreds of qubits. I think that the most advanced demonstrations are in this type of technology, specifically, I think by Quera, the company by Vladan Vuletic and Misha Lukin. So they have amazing demonstrations, but they're still the hundreds. And it's a big challenge to go another 3-4 orders of magnitude to the millions. So what do we have? We barely have one logical qubit if we look at material qubits. And in that sense, we're not better than we were 100 years ago. 80 years ago. So Alan Turing and the guys and everyone at Bletchley Park, they broke the enigma and saved World War II with a mechanical computer. So what all the quantum computers we have today are not cannot help the world, cannot help mankind the way a mechanical computer helped 8 years ago. We cannot do this with a with any quantum computer today. So we are very behind in terms of scalability. And people hope to have some kind of Moore's law, but Moore's law kicked, in the beginning, it was by changing switching technologies, and it started really picking up with a lot of effort and budget only when a scalable, a cut and paste technology emerged. So quantum computing is not there yet. We're still in the hundreds. So what we need is something that's scalable, and that led to the last emerging direction, which is a photonic quantum computer, where the computation is done with photons, particles of light. And and photons are inherently something that you can distribute and multiply many times because photons do not affect other photons. Light can go through light with no problem. So the way a photonic quantum computer works is you start with a machine that is called a resource state generator. It's something that generates small clusters of those photons that are entangled together. And you send them to a delay line in fibers, and that's already your cut and paste in time. You send a group of photons, send to a fiber. And while they're still in the fiber, you send another group and another group. This is not something you can do with material qubits, right? You cannot prepare qubits, put them on the shelf. Prepare qubits, put them on the shelf. They will be destroyed on the shelf. With photons, you can prepare photons, throw them in a fiber, prepare photons, throw them in. So that allows you to do cut and paste in time. And of course, you can have many of such sources, and then you have cut and paste in space. So this shows you why photonic quantum computation seems like a very, very good candidate for scalability. The problem is that the way that it was attempted until a quantum source, until recently, is generating those small clusters is actually very, very hard. And current methods are so inefficient. How inefficient? One in a million. So the largest, I think, quantum company worldwide, and certainly one, in my view, the most promising one is PsiQuantum. And they're building two sites, one in next to Lake Michigan. You see Chicago there in the horizon, and one in Australia. And the quantum computer, the photonic quantum computer they are building, is at the size, of a fab, a few football courts. It's like a big plant. It has its own power plant, helium liquidation plant. Why? All of that because generating those clusters of photons is very, very inefficient the way they do it. And actually, I was part in a due diligence process. I was involved in a due diligence process regarding PsiQuantum in 2018. And when I flew there, I realized how crazy they are, but actually that they're the first ones that I think will reach the millions of qubits. So I was very excited. And actually, when I visited them, the head scientist there, Terry Rudolph and Jeremy O'Brien, the CEO, they told me, "You build this, we buy it for a lot of money." And I said, "Okay, I'm listening." And they explained the problem, and they helped me realize how important it is to do a deterministic source of photons, a deterministic source of entanglement photons. And the way to do that is only with a single atom. So single atom can do gates with photons, can generate single photons and can entangle them together. And why did they approach me? Because if we go back to the 2012 Nobel, so you see Dave Wineland and Serge Roche. So actually, Serge Roche got the message about him receiving the Nobel Prize when he was on his way to visit the Weizmann Institute. So see him there with a much, much younger and thinner version of me. My lab was still, in its infancy there at Weizmann. And the reason he visited specifically my lab is because my lab is at that time was the only place worldwide in Weizmann that dealt with connecting light photons. What you see here is a chip-based resonator. It's like a sphere connected to a fiber. So connecting light with atoms. So photon atom gates. This is what we attempted there. It was very ambitious. And actually, he encouraged us very nicely. And between 2012 and 2018, luckily, we had our breakthrough, a series of demonstrations of these gates. And that led eventually in 2018, both Serge Roche and actually his advisor, Claude Cohen-Tanuji, who got the Nobel as well. They visited my lab in 2018 after we already succeeded all those things. But what's more importantly, or even more life-changing for me, is the fact that it led to the establishment of quantum source. So together with Oded, was actually the founder of Altair, and then the head of Sony Israel, and Gil, who actually was responsible for the architecture of the M1 chip in Apple, and Dan Harash, who was the co-founder and CEO of Provigent, who was sold to Broadcom. So together we decided to go on that adventure and try to build that technology of deterministic generation of photons. What you see here is actually the heart of our technology, the heart of our machine. Inside that vacuum tube, you see this is a real image of a cloud of atoms held by lasers. And each 5 seconds or so, we send a group of atoms to a chip on top. And this is the how we trap the atom on that chip. We have atoms trapped. Today we trap them for seconds. You can finish your coffee, if it's cold, while still the atom is still trapped. And now we're going into we started an effort of commercializing this product. It's supposed to come by 2027 to have the first compact source of those clusters. And the idea is that not many atoms would stitch the code, the code I showed you, with many photons. So the atoms are like the needle that is sewing a large fabric of photons. And we have a paper about that, and we have upcoming papers with experimental results. And this is it. Quantum source we have raised 77 million. By now we have almost 70 people. More than half of them hold PhD. So in many ways, so what we build today is no one else on earth has that technology, or is for better or for worse. It's hard, but we're the only ones worldwide that's doing it, and that's the Israeli chutzpah, we hope. So this is it.